All right, let's talk about predicting the future. It's something we're all a little obsessed with, right? Whether it's the weather or the stock market. But what if I told you one of the most powerful prediction tools out there is actually based on something you definitely learned back in middle school math? I mean, think about it. You pull up a real estate app, pop in a few details about a house, and boom, out comes this incredibly specific price. It feels like magic, doesn't it? Well, it's not magic. It's actually a classic example of a prediction problem. And once you start looking, you see these problems absolutely everywhere. We're talking about forecasting sales for major companies, estimating what your medical bills might be, even predicting a salary for a job you're looking at. It's this quiet, foundational tool that's constantly shaping our world. So what's the big secret? Well, the answer, believe it or not, starts with a simple straight line. Yeah, that's it. The technique is called linear regression, and it's this surprisingly elegant solution to all those incredibly complex prediction problems we just mentioned. So, at its heart, linear regression is all about sifting through a huge mountain of data to find one single, perfect line that describes the relationship in that data. The whole goal is to draw one line that can help us make really good, educated guesses about things we haven't seen yet. Now, it comes in two main flavors. You've got simple linear regression, which uses just one piece of info to make a guess, like using only the square footage to predict a house price. Then you have multiple regression, which is way more powerful. It uses two or more things, like your years of experience plus your degree, to predict salary. To keep things clear, we're going to stick with the simple version today, just to really nail down the main idea. And this is the recipe for that line. I know, equations can look a little intimidating, but trust me, this one's our friend. Think of it as just a simple set of instructions for drawing our prediction line. Let's break it down piece by piece. Okay, first up is why. This is the big one. It's a thing we're trying to predict, the answer we want to find. So in our housing example, y is the final price we're trying to figure out. It's our target. Then we have x. This is the piece of the puzzle we already have. It's our input, our main clue. So to predict the price, our x is the information we know for sure, the house's size in square feet. So what about these b guys? Well, b0 is the intercept. Just think of it as the starting point. It's the baseline price of a house before we even consider its size, like the value of a house with 0 square feet, if that were possible. It's where our line begins. And now for the real star of the show. B1, the slope. This is the magic number. It's so important because it tells us exactly how strong the connection is between the size of a house and its price. It answers the question, for every extra square foot we add, how much does the price go up? That's the slope. Okay, so the computer's job is to find the perfect intercept and that perfect magic slope. But here's the thing, there are literally infinite possible lines you could draw. So how in the world does it find the one that is the best fit? Well, the goal is actually super intuitive. Imagine you plotted every single house you have data for on a graph. Size on one axis, price on the other. You'd get this big cloud of dots, right? The algorithm's only job is to thread a single, straight line right through the middle of that cloud that gets as close as possible to all those dots at the same time. It does this by obsessively measuring something called error. An error is just a fancy word for the distance between the line it drew and where the actual data point is. The goal is simple. Shrink that distance. Make the grand total of all those little errors as tiny as humanly or, well, computationally possible. And the specific method for doing this is called ordinary least squares, or OLS for short. That squares part is the secret sauce. By squaring the error for each point, the algorithm really punishes big mistakes. It's like a teacher who takes off way more points if you're totally wrong than if you're just a little bit off. It forces the line to be a good, honest fit and avoid those wild misses. But you can't just throw this technique at any old data set and expect it to work. For our predictions to actually be reliable, the data itself has to follow a few really important rules of the game. So for this to work, there are 5 key rules. First, linearity. The relationship has to actually look like a straight line, not some crazy curve. Make sense? Second, independence. Each data point can't affect the others. You can't say survey one family on their favorite TV show and pretend you have 5 independent opinions. Third, homoscedasticity, and I know, that is a mouthful. It just means our mistakes should be random and evenly spread out. Our model shouldn't get worse and worse at predicting as prices get higher. The last 2 rules basically just make sure our errors are random and that we aren't using the same information twice. If you break these rules, your prediction line just isn't trustworthy. Okay, so we've built our model, we've followed the rules. The very last step is to figure out, is it any good? How do we actually grade its performance? We do that with a metric called the R-squared score. The easiest way to think about this is like a report card for our model. It gets a grade on a scale from 0 to 1 that tells us how much of the story our model is actually explaining. And it's pretty easy to understand. A high R-squared, something like a 0.90, is like getting an A+. It means our line explains 90% of why the prices change. That's fantastic. But a low score, like 0.15, that's a poor fit. It means our super smart line is barely better than just taking a wild guess. It's not very useful at all. So as we start to wrap this up, it's pretty clear that linear regression is a fantastic tool. It's simple, it's powerful, and it's easy to understand. But it's not a silver bullet. It has some really important limitations you have to know about. On the plus side, it's simple and it's fast, and you can look right at it and see exactly how each part affects the outcome. But its biggest weakness is right there in the name. It only works if the relationship is actually linear. And it's super sensitive to outliers. Just one or two crazy expensive houses in your data can completely throw the whole line off course. But even with those limits, its raw power and simplicity make it an absolute workhorse in pretty much every industry you can think of. From business and real estate to finance and healthcare, this is often the very first tool a data scientist reaches for to start making sense of their data. It's kind of amazing, really. This humble, straight line, something we all learned about years ago, is a true cornerstone of modern AI and data science. It really makes you wonder, what other incredibly powerful ideas are just sitting there hiding in plain sight, waiting for us to see them in a whole new way?